In Part 2 of Lecture 12, we will discuss low-level input-output operations. There are two different methods for handling the interaction between the host system and the device controller. The first of the two is called polling. Any resemblance between this method and the way opinion polls are done is purely intentional. This is done in 6 steps, as seen on the slide. Step 1 is where the application requests that a byte be written on the output device. This request is handled by the write function for that particular device. Obviously, if this device is a printer, there will be no read function, and if it is a keyboard, there is no write function. Step 2 involves the host checking the busy bit in the status register continually until the bit is cleared. Cleared means that it contains a value of 0. In step 3, the host sets the command register's write bit. Setting a bit means giving it the value of 1. In step 4, the host writes the byte being written into the data out register. Step 5 involves the host setting the command ready bit. In step 6, the controller reads the command register, sees the write command, reads the data out register, and does the output operation. In step 7, the controller clears the command ready bit, clears the error in the status register because the operation succeeded, and clears the busy bit because it is finished. The process concludes with step 8, where the data is written back into the memory space belonging to the operation. The biggest problem with this process is that we make the processor wait for the device to be available. Since so many devices are so much slower than the processor, this wastes an enormous amount of time. It's like my turning on the tea kettle and running back and forth from my home office to my kitchen to see if the water is boiling yet. I'll spend so much time checking it, I won't get anything else done. Interrupt-driven I/O works on the principle that instead of constantly checking the device, we will wait for a signal from it. That signal is called an interrupt because it is interrupting whatever the processor is doing. If I were still trying to make tea while trying to work, it would be analogous to putting a whistle on the tea kettle. I no longer have to keep checking the tea kettle because I am confident that the whistle will get my attention. In the example on the slide, the process starts with the application requesting a read operation in step 1. In step 2, the driver determines the busy status of the device. If it's busy, the driver will wait until the device is idle. In step 3, the driver writes the input command into the device controller's command register. Before terminating, the driver's top half saves the relevant information about the operation in the device's status table, indicating the return address of the original call and any special parameters that the I/O operation might have. This is step 4. This allows the process to continue when it rescheduled on the processor's ready queue. The operating system can now turn over the processor to another process, while this one waits for I/O to be completed. Eventually, the device completes the I/O event. When this happens, it signals the processor, and the interrupt handler starts running. This is step 5. In step 6, the interrupt handler determines which device triggered the interrupt and starts its appropriate device handler. In step 7, the device handler gets the status information from the device status table. Step 8 takes place in 2 parts. data moves from the controller's data register to the device handler's data area, and from there it moves to the application's data area. Lastly, the device handler returns control to the application, which eventually regains use of the processor. Interrupt-driven I/O is no faster than pole-driven I/O. The big advantage is that while we wait for the interrupt to be handled, the processor is busy doing other things. This is more efficient because of the higher throughput. Not all interrupts are equal. Some are crucial to the smooth operation of the system, and others are less urgent. As we learned earlier when we were studying process synchronization, there are some segments of operating system code that we cannot afford to interrupt. If they are not performed as a unit, the integrity of the system is threatened. But there are certain interrupts that are more important than others. Most processors have two interrupt lines. One for unmaskable interrupts for events too important to miss, such as memory exceptions, division by zero, and invalid opcodes. The other one is for maskable interrupts, which we will mask to avoid interrupting critical sections. On most computers, an interrupt number is an offset from the beginning of the interrupt vector. But the interrupt vector can get very large if there are a lot of devices. The main alternative, one general interrupt handler, which checks each device, doesn't seem much better. We can waste time or we can waste memory. A common compromise is interrupt chaining, where each item of an interrupt is a linked list of interrupt handlers. This limits the size of the interrupt vector and limits the number of devices that must be checked. Programmed input-output, where we transfer data 1 byte at a time into a controller register and then use a general-purpose register to watch its status bits, seems like an awful waste, especially when you consider how much data we are moving these days. Back in 2001, JPEG files could be 100 kilobytes, and audio files, like the one that you're listening to now, could be close to a megabyte in size. These days, they can easily be 10 times that size. Moving that much data 1 byte at a time would seem to take forever. Direct memory access, or DMA for short, gets us around the problem. We use a specialized controller called the DMA controller to move data directly into memory. The transfer process begins when the processor tells the device driver to transfer from the data so many bytes to a buffer at address X. The device driver then tells the disk controller to move Y bytes from the disk into the specified buffer area. Now the device driver initiates the DMA transfer, sending each byte to the DMA controller. The DMA controller, in turn, sends the byte to the buffer, incrementing the buffer address and decrementing the byte count until the byte count is down to 0. Then the DMA controller signals an interrupt. Generally, this is done for processes by the operating system, because most systems do not wish to give such control of the hardware directly to applications. And for good reason. An application with an error in it or written maliciously could cause damage to itself, to the system, and to other processes. It's initiated by the host system writing a DMA command block into memory. This command block includes a pointer to the source of the data being transferred, a pointer to the data's definition, and the number of bytes to be moved. After doing this, the CPU writes the command block's address to the DMA controller and goes back to its own work. then the DMA controller takes over the job. The DMA controller and the device controller need to perform a handshake. This is done by the device controller transmitting the DMA request signal. The DMA controller answers with the DMA acknowledge signal and removes the DMA request signal. And then the transfer begins. When it's over, the DMA controller interrupts the CPU and signals that the operation is complete.